All right, so now that we've seen how to use the nearpoint function, let's go a step further and talk about nearpoints as a function, which gives us back not just one point, but multiple points. And in that vein, we will start to talk about arrays. And when we talk about arrays, we also have to talk about the Foreach loop. So what we have here to slowly get into this is a problem that you could solve with minpos and nearpoint. So the problem we're trying to solve here is that we have a sphere, and to make it a bit easier, we just scatter a couple of points on this sphere, and for each point we want to create a line to the second sphere. And what we could use for that, for example, is we could use minpos to find the closest point on the surface of the second sphere, and then just create a polyline out of the point that we're looking from to this point that we found. That's perfectly fine and that works, but what you can see is it tends to, give you a certain look because each point will have a similar likelihood of finding a certain position. The whole thing works better if you have a different scaled object, then I guess it makes a bit more sense. And of course, what you could use that for is some kind of, spider web system or something. Another option for this is using a nearpoint, and here we would use the idea of scattering on one sphere. Here it is. There you go. And then a second sphere over here. Let me rotate around like this. We would not try to find, the nearest surface point on this, but we would scatter our own points, which would have the advantage of us being able to more clearly define where a potential connection could happen. So what we're trying to do really is we try to connect those two point clouds. And of course, the code for this could look something like this. Each point on the first scatter cloud, like this one, will look for the nearest point of the second input, which is this cloud, and then finds that, reads from this point number that it gets, the attribute p, and then creates a polyline like we saw before. I'm not saying this is better or anything, it's just a different way of solving this problem, and let me try to show this somehow. And here you can see, which is interesting by itself, it will always only find specific connections between specific points. Of course, there are different ways of doing this. For example, you could just find random points and all that. But this is exactly kind of what we want to talk about. What if you have the problem that you don't want to have the nearest point, but something else? And this is solvable with the nearpoints function. So actually, let's take this example, and instead of trying to find the nearest point, we want to find a couple of points that are close enough to us. So not points back here, but maybe, the first 10 points that are the closest, not just the first one. And then from this, we choose a random one. This could be interesting and would be a bit more closer to how the spider web would probably look like. What we can use for this is the more advanced version of nearpoints. And the problem we're facing now is that this will return multiple points. And you can tell from those weird brackets here. What this gives back is not a single integer point, but a group, or we also say an array of multiple points. First of all, let's just read this out so that we understand better how this looks like. Let's bring it back. The syntax or the logic is very similar to what we've seen before, so it's quite straightforward for us. We just take the second input. We want to look for the closest ones relative to the current position. And then there's the option of a maximum distance. I think we ignored this in the last video because, we're only supposed to find one point. But in the moment we want to find more points, having, a certain distance in which we find them makes a lot of sense. Because otherwise, of course, we would find all the points that are near, which are all points in a way. They are, all points are the nearest points if there is no limitation. So let's put in this limitation and use the max distance function. And we put this onto a parameter here, and we will play around with this later, but let's set this to, 3 meters for now. Now, the function, of course, gives back something, and as we've said, it gives back a list. So just for fun, let's use a normal integer. Actually, let's do it as an attribute. An integer, it's called a new point, and see what we get. And we will actually get an error. And what it basically says is this will not work because it's a near points and you have to put this into an array. So let's start how to do this with attributes. And it's actually relatively simple because it's similar to what we see here. Right after the definition of the data type, you put in those brackets and then it works. And here you can now see what it means to have an array. It's just a long list of all the numbers it found in a certain distance. And if we lower this, of course, a meter is too short, as you can see. Now, no point here. Let's see, no, none of them. None of them finds any point of the second points in the distance of 1 meter because they're probably too far away. So let's try 2 meters, and now it finds way more. And if you dial them down manually, you can see it finds, each point finds more or less points. Remember, those are the point numbers of these points over here. So if, let's say you wanted to do this not with attributes, but with internal variables, then the logic would be the following. You use integer and then you don't put this next to the data type, which is a bit weird because that's how this looks like. You would put this into the name of the variable. So let's call this Nearpoints, for example. And to declare that this is an array, we put the bracket at the end of the name. So it's a bit weird that internal variables work differently to attributes, but this is how you do it. So for now, let's stick with the attributes because it's a bit easier to use for now. And now the next question is, okay, how do we handle this? What do we do with this? What we could do in theory is we could create a new prim. In the current geometry, you want to create a polyline, let's say. And we could actually, if we wanted, create a line with all the points included that we just created. And this would look like this. Okay, this is wrong for many reasons. So what you can see here now is currently that each point creates actually multiple lines and connects it with all the point numbers that it found from near points. But the first thing that is wrong about this, and this is why the connections are created here, is it uses the point numbers from the second input and applies it to the first input. And there is no way to do it any other way by default. The second problem with this is, of course, we now have lines with multiple points in it, and that's not even remotely what we wanted. So here's the solution for this. To run basically through all these points, you need a for loop, but not a for loop that we already know, but a for each loop. Now, a for each loop allows you to run over a list of things and do something for each of the elements. Basically like the for each loop we know from the sub level, but this is to use it inside of Vex. And the logic is you first give it a reference attribute that it uses where it fills in each of the elements, and then you give it the array that you want to run over. Then you need curly brackets to define what's supposed to happen here. And then in here, you put in the command you want. So for example, for the current geometry, we want to create a new polyline and we want to feed it our current point and a new point that we haven't created yet. So let's first do that. And then we will talk about this again. I think it makes the most sense to do this first. And here's actually the advantage. What we want to create as part of the polyline is a point on where the other sphere is. And here you can now see what the advantage of this concept is. We can actually read out an attribute from each point that we found, not just the first one, but all of them. And here we finally use this I that we created before, because currently, like I said, what's happening here is happening to each point that our near points found. That's what for each means. And the current point we're running over that is in this list here that we filled is represented by I. So this code will be run for each point that is found, and the current one is represented with I. This is what this here means. So let me finalize this like this, and then we can talk about this a bit more. So here's what we have. So what's happening? I think it's a bit easier to understand if we lower the number of points on the first sphere, to only 3, let's say, and then it looks, for example, like this. Yeah, that's pretty good. So this is the result for a single point, even though we have 3. So first of all, what happened here is only this point of the 3 we have found points in the distance we declared with 1 for 4. If we would lower this, none of them would find anything because those points are too far away. And if I would increase that to 2, then all 3, there you go, would find a lot of points. So let's play around with this. Maybe then you can see it better. If I lower the distance, the potential distance in which distance the first points can find near points, then this changes, of course, the results. So let's keep it like this maybe. And the reason we have multiple connections now for each point is that we run through all these points that were found with a for each loop. And the way this works is you give it the list or the array that you created and then a reference variable. And this reference variable represents the current point we're running over, and each of these lines here in the curly brackets will be run for each point. And what's happening here is for the found point, we read out the position of that point with the point function from the second input. Then we create a new point on that position, and then we create a line between the two. That's what this means. Now, this is a perfect example for actually something we might want to add to this, because currently we will always have multiple points that we find in a certain distance. So what do we do if we want only one connection, or maybe let's say 2 connections, because then we have something different to near point. We will never, of course, find a distance that is correct for all 3 points where all 3 will find 2 near points. That's impossible. And this is where the 4th optional input comes in, the max points. And this is really helpful. And for now, I do it hard-coded. I just add (2) to this, which means no matter how many points you will find in the max distance, you will never find more than 2. So let's increase the distance now. And here you can see each point will maximum find the 2 closest points, or maybe the 3 closest points. And this is how we can control this. And as you can see, that's pretty interesting because now we have more control over what points are found, and we can also use more points. And here you can see now the idea. We can now connect multiple points, not just one. And this is what you can use the near points for. We can even add the max distance so that we can say, okay, but further than a certain distance, there will not be a connection, only if we go closer. So this is pretty cool, and this is what you can do with the near points, which is only possible because you can basically choose from multiple possible near points that you find. Let's look at a different example where we can use near points. So let's say we wanted actually to have a simpler version of this. So we don't even want to have multiple connections, but really just, one per point. But now we have the problem that we have multiple spheres. And what we want is not a single sphere to be connected to some other sphere, but each sphere should find the closest connection relative to the closest sphere it finds. Now, at first, that seems to be easy because we could do this with a near point function. So let's just use a normal near point function. And now that's the first weird thing. We don't have a second input because we want this to happen for each point of each sphere. Actually, what we could do to make this a bit easier is to scatter a couple of clearly defined points on the surface. And now we can't use a second input, even though we could, sure, but it would be the same as the first input. So this time, we try to find the nearest point of the whole geometry relative to our current position. And this would actually give us something. So if we quickly try this, if we want to create a new line to that point we found, we don't even have to create a new point because this point already exists in the geometry we are running over. So we can simply say, okay, create a polyline, please, between the current point and the nearest point you also found in the same point cloud, which is a near point. And let's see what happens. And something strange happens, and that is it actually created 1,000 lines. There you go. We still have the points, and even though you can't see it, there are actually lines. Now think about what just happened for a second. For all those points, from a particular point like this one, we are looking for the closest point in all those points to this point. And you would think we would find, I don't know, this point maybe, or this one. No, we find the same point. Because in this point cloud, the closest point is the point itself. So you will need at least one more point And this is where Nearpoints comes in as a solution. So let's do this. And as we said, we need an array for this, so some kind of list data type where we can save multiple points. And just to be safe, let's do this in an attribute again so that we can actually debug this and see it down here in the geometry spreadsheet. And before we create a new primitive, let's run this first. And it complains because there's something missing, but it needs at least a max distance. So let's use this with our own parameter. And we want to limit it to a certain extent. And here you can see that it works. If I dial this up, it finds, even on, with a max distance of 0, actually I should have done this before, you can see it will each point will always find a single near point itself. So as soon as we dial this up, it finds more. So at least 2, hopefully. And now what we want to do is, let's say we can actually use this, but this time we will connect to the second best point it finds. And for this, thankfully, we don't even need a for each loop if we don't want to. We could actually just use from the near point. Oh, it actually should be near points, sorry, which is now an attribute. This is a list. From a list or from an array, we can actually take a particular part by adding brackets behind it and then a number. And this is the same logic as the input into a node. The first element would be 0. And this will work again. And guess what? The first element, like we remember, was always the point itself. And what we wanted was the second one. So of course we take 1 inside. And now this happens, which is still not what we wanted, unfortunately. Damn it. Okay, but at least we have curves now. And that is, it finds actually the second closest point. Let's take the third closest point or the fourth closest point and so on. You can see the problem. It will always find the closest point because the closest point will always be on its own sphere, probably. So how do we solve this problem? This is now actually where we need the for each loop, because what we can do with this is we can add an additional information to separate those spheres. And for this, we can use the connectivity node, for example. So up here, the geometry is still together as geometry. We create a class attribute, scatter on those, and then those points have their class attribute. So the order is important, of course. And now what we can do is we run over the points we found again with a for each loop, of course. And the array is called Nearpoints. There you go. And let's make sure that we're not creating, a primitive with the fourth point we found, but actually with the current point that we run over right now, which is an I. And now currently it would create a primitive again for all the points it finds. But what we want to check now is we want to read out with a point function the class attribute of the point of each point we're running over right now, and then compare it if it's the same as the class attribute of the current point we're actually on. And if it's different to our current class attribute, in other words, if the point we're running over right now is on a different sphere than us, only then do we want to create that curve. Unfortunately, there are no connections. Why is that? Well, because our max distance is too low. So the amount of points that it finds here, which is quite a lot actually, is potentially, probably, all the points that each point found are still the points of the same sphere. So they all have the same class attribute. And to find more points, there we go, that then are actually part of another sphere, we have to increase the distance. So I think you now start to understand why this is under advanced and not basics. But I hope you understand at this point why this is an important technique that you need to understand. By the way, sometimes, like now, we have again the problem that each point finds multiple points where this check here is true, because there are multiple near points potentially with a class attribute different to my own one. Now, what you can do here simply is, if you found this the first time, you can just stop the for each loop. And the function for this is called break. And if I do this, you can see now we only find, each point only creates one line, because once this is not true, so the first time it finds something with a different class attribute, it creates the primitive, the curve, and then it stops the whole process. So break is relative to the for each to stop the for each loop. We don't need to find another point. We're done. So yeah, here we go. To be fair, it's not really sexy. It looks a bit crap. But at least it does what we wanted it to do. It only finds points where the class attribute is not identical with its own one. In other words, it will only create connections with another sphere, never with itself. So this is a problem that you could not solve with the knowledge we have so far. And if you think about it, even a min-pos wouldn't have worked here, because a min-pos also would find its own sphere. So you would need to use the same kind of technique by using a for each loop. So it will not help. So yeah, I think I will stop here. Think this through a little bit. What we talked about is near points, which instantly makes everything more complicated, because instead of finding just one point, we find multiple points. But the advantage of this is that we can now run over those points with a for each loop and make certain decisions based on what we found. This is much more complex than what we saw before, but it's also much more powerful, of course, and this is the whole idea. So we learned how to work with arrays, we learned how to work with the nearpoints function, and we learned how to work with for each. Before I finish this video, one small add to this. There is a very similar function that works in the same way, and that is the PC find function. In the next video, we'll talk about the PC open function, which is kind of, let's call it a sibling of the PC find. Here, the main difference is that you have a reference channel and a reference value, which usually is P as well. So it's slightly different. But when you look here at the example of the VEX documentation, you will see that the logic is very similar. It also uses a for each loop to run over the points that the PC find found. And it uses a max distance and a max points. And even though the file name might be a bit confusing here, actually you would be able to just put 0 here for the geometry. So this is very similar, but the good news is here, Nearpoints actually is as fast, to my knowledge, as PC find. So if you use that, it's totally fine. And in my opinion, it's also easier to understand because the name Nearpoints is already self-describing. So if you find someone using PC find, it's basically the same thing. It's just an alternative version of that. And feel free to read more into this, but the concept is the same. Okay, so let's finish the video here. But before we do this, let's quickly apply what we learned so far by copying this note here to a bit nicer example so that we have a nicer preview of the whole thing and maybe something that is closer to a real world problem. So I have a couple of branches here that I want to use with our new technique here, and they are separate geometries, of course. And we just do the same that we just did. We create the connectivity node so that we have a class attribute. We then scatter some points on it, and then we drop our VEX code here, and it should work just the same. Let's lower the distance, and then here you can see why this is cool. Let's actually merge this. And here you can see now if we increase the distance, and what I noticed, because the viewport as usual creates a lot of trouble, for some reason it didn't work with the high quality lighting. I had to go back to the headlight only lighting, but doesn't matter. So now we can see what this does. Of course, the VEX script only finds connections to objects or points on the objects that don't have the same class attribute. So a really interesting approach and something you can do with arrays. And here could be a possible use case for this for some kind of spiderweb system. So I hope this is helpful. Thanks very much and see you later. Cheers.